So let's start right off then with the first step. We want to determine then the ordinary differential equation for Q of R. And again, just to remind ourselves, the strategy is to use the fact that rho of R is equal to R to the L plus 1 times Q. Now I'd like you to notice that I'm not going to keep writing the fact that these are P and rho and Q are functions of R. I think we know that from context, and this is going to help minimize the writing. So I need to substitute this now into my time-independent Schrodinger equation, and doing that requires access to the second derivative of rho. So we're going to calculate that. Also in a step-by-step procedure, we will begin by taking the first derivative of rho. So the first derivative, by the product rule, I have the derivative of the first term. So L plus 1 will come down. I will then have R to 1 fewer power L times Q. And then the second term has the first term, R to the L plus 1, times the derivative of the second term. And the second term's derivative was just, of course, Q prime. Continuing along then, of course, I could write rho double prime. I now need to take a second derivative of something that is a sum of two products. So in the first case, once again, we'll be taking first the derivative of the first term here. So I'll have L plus 1 times an L comes down now, R to the L minus 1, multiplying Q. Plus then I have the case where the derivative hits Q instead, which will just turn it into a Q prime. So I have L plus 1, R to the L times Q prime. Next, I need to take the derivative of the second term in the sum, which is again a product, the derivative of the first term of which will give me an L plus 1 times R to the L, and that's still multiplying Q prime, but you will notice that's exactly the term I have just written down. And this is actually a pretty common feature that we find in taking second derivatives of products. You always end up with twice the cross term of the derivatives. Finally, we have the last term where the derivative hits the Q prime. That is pretty easy to write down. The first function stays as it is, and the second one I then get my Q double prime. Now, I need to substitute this into the time-independent Schrodinger equation. Before doing that, it helps to organize myself. The TISE will also have these factors of rho, which all are written down as R to the L plus 1 times something. So to stay organized, it's really going to behoove us actually to factor out that R to the L plus 1. So let me factor that out as one grand factor. Also, I like to write my derivatives in descending order so that I have the more complex things first. So let's do that. So the R to the L plus 1 I've factored out. So the first term is Q double prime. My next term with the Q prime has these factors, but it's only R to the L. So therefore, I need to factor out, if I factor out L plus 1, I have a 1 over R left over. So there's going to be 2 times L plus 1 divided by R times Q prime. So that when I multiply this out, I recover my R to the L. Let me just make sure I write that as an R to the L a little more clearly. And then finally, I have my last term. It's really R to the L minus 1, so it's going to have an R squared in the denominator. So this will be plus L times L plus 1 all over R squared, and that then is multiplying my Q. Now, finally, I'm ready for the time-independent Schrodinger equation. So when I substitute in there, I need to have minus 1/2 the second derivative of rho double prime, which has this nice factor of R to the L plus 1. All of my rho terms also have that factor, so I'm going to just factor out right at the beginning this term that's going to be common to everybody. Next, I need minus 1/2 rho double prime, so I will then have minus 1/2, I factor this piece out, each of the terms here on the inside. So that will give me minus 1/2 Q double prime. This term, the 1/2, will kill the 2. I still have the minus, so minus L plus 1 over R, which is multiplying Q prime. I then have minus 1/2 L times L plus 1 over R squared, multiplying Q. So that's my first term in this Schrodinger equation, right? My minus 1/2 rho double prime. I now have these two different potentials that are multiplying rho. So I need these two factors then multiplying R to the L plus 1 times Q. I've factored out the R to the L plus 1, so I just need those two factors multiplying Q. The first factor is my centrifugal potential, which is L times L plus 1 over twice R squared. That's multiplying Q. And then the other piece of the potential that I have is minus 1 over R, which also multiplies Q. And finally, the right-hand side of my equation is going to be E, the energy, times rho of R. So I need to include E times rho, but rho itself, once again, has this nice R to the L plus 1 times Q. Woof, that was a lot of algebra. Take a little breather here. And let's look at how we might be able to simplify our expression. The first nice thing is because of the way we've organized ourselves, notice these R to the L plus 1 factors all disappear. And then I'm left with something that looks a lot like a Schrodinger equation. I've got a kinetic energy term, I've got an energy times my effective wave function Q, and then I have these additional terms on the inside. But you will notice something really beautiful is happening here. This extra term, which we generated by picking this form for rho, right? The whole job of the R to L plus 1 really was to generate this term, because this term exactly cancels this term, which is the centrifugal potential. So we actually did pick out the right factor here, because by including it, it has simplified the equation that Q obeys. It simply does not have these two terms. There's no more centrifugal potential. I do pay a small cost, which is now I have this additional first order term, but that definitely I would regard as progress. We have a much simpler equation here.